This is a video on difference and how you can use Excel to find the percent difference for every data point in your graph. Now, just a refresher, this was my independent variable, right, mass, and then I measured 3 trials for final velocity. So for every mass, I took 3 trials, which aren't shown, of the final velocity, and I averaged each of those, which is shown here. And ignore this, I put in numbers here, but really it would be an equation like equals average, and then it would have the 3 cells for the 3 trials highlighted in the middle. So this was my independent variable. This is the average of my dependent variable. Here are my uncertainties in the average values, so this is the uncertainty in my dependent variable. And then I found my power relation. I found the value of the exponent or the power to be 1.3. And I raised every one of these masses to the 1.3 power, and this is what I get, right? And here's the uncertainty in these values. So on my final graph, I have mass to the 1.3 on the x and average final velocity on the y. For every single data point, and then here's my line of best fit, and here's the equation defining the line of best fit, or the equation of the line. For every data point in this graph, there is the actual y value, right, which is what's shown in this chart. But then there's also a predicted y value. In other words, if I take 1, right, which is the x value for my first data point, right, 1 is the x value for the very first data point, shown here. And if I plug 1 into this equation as x, then I would calculate a predicted y value. And when I say it's a predicted y value, I mean it's the y value predicted by this line, by this best fit line, right? So I'm going to do that for every single data point. I'm going to say equals, and I'm going to do 4.8011, which is the number shown here for slope. And I'm going to multiply it by the x value. I'm going to add 11.069, and I'm going to copy this down so that every single one of these x values is substituted into the equation, producing the predicted y value. And I'm going to call that predicted, and I shouldn't say y value, that's just my informal language that I'm using. I'm going to say predicted v average, right? And I'm going to highlight average, font, I'm going to make it subscript, if it ever pops up. And here it comes. The suspense. Oh, the suspense. Uh-oh, not responding. Here we go, finally. Subscript, that's all I wanted. Was that so much to ask? And I'm going to italicize it. And let's see. I should really have units, so I'm going to come in and say meters per second, but now I have to highlight and de-subscript this. So font, and obviously it's quicker the second time. Okay, and I don't want this italicized either, so I'm going to Control I there. Now I want this merged and centered, and I center, and it should wrap onto the next page, onto the next line. And I'm going to put a box around it. These values all came from my masses, right? My mass to the 1.3 power, which all of those had 2 sig figs, which means these all must have 2 sig figs. So let me take away some numbers here, some decimal places. There we go. Now, the final thing that I need to do, now that I have all of these predicted average velocities, average final velocity, and really, let me fix this. Average shouldn't be in there. This is the predicted final velocity, like that. For each of these values, we can calculate a percent difference between the true, or the actual measured final velocity, the average, and the predicted final velocity. So here's how you do that. You take the difference between the two, so this minus, this minus this, and you divide by the average. So you divide by average this, comma, this. Close the parentheses, and we want this as a percentage, so I'm going to click the percent button, and I'll add a decimal place, why not? Drag it down, box it, and let's center. Now I'm going to copy this over to here so that I get all of my formatting copied over, so I don't have to go through the rigmarole of merging and centering, of blah blah blah. And this is the percent difference. And it tells me how far off is the predicted value from the actual value that was measured as final velocity. And with these percent differences, every one should be positive. We don't have negative percent differences. I mean, you can have a negative, but we just make it positive. So there's an absolute value function which we could add in to each of these, like that. And now I'm going to copy it back down, and there we go. No border, clear it out, and then give the outside border. So this is how you find the percent difference. Okay, what I would put into my lab report is these two columns of data, and then maybe I would discuss, in general, the percent difference ranges from 5.6 to 0.5. Wow, that's really good. And 5.6 is a pretty low percent difference. Anything below 15% is pretty good. So you might discuss this in the report and show that, this indicates that the model, the line of best fit, is a valid model for the data, and you describe it in that way, in those kinds of terms, right? You would show one sample calculation. You would have to show a sample calculation for finding the predicted value. So you would have to show that just once. So write it out with the equation here, write this equation out, and show your work plugging in the x value. And you have to include units there. So that's annoying because the units of the x value are grams to the 1.3 power. That's the unit of the x value. And then for percent difference here, you would have to show one sample calculation where you found the average value and the difference, and you took the difference and divided by the average. You would have to show a sample calculation of plugging into the equation and finding the answer. And don't forget to multiply by 100% in your sample calculation. So that's how you do percent difference using Excel.